on subgroups in group theory. First of all, what do you mean by a subgroup? In group theory, a subset which satisfies all the properties of a group G is called as a subgroup of G. What is the property of groups? A group means it should be closed under a binary operation star. It should be associative. It should satisfy associative law, and then there should be an identity element in the group, and inverse element also should exist in a group. So, if a subset H satisfies all the properties of a group G under the binary operation star, then H is called as a subgroup of G. So, in group theory, given a group G under a binary operation star, a subset H of G is called a subgroup of G if H also forms a group under the binary operation star. A subgroup of a group consisting only the identity element singleton E is called as the trivial subgroup of G. Now comes a theorem. If we are given with two subgroups H and K of G, then H intersection K also forms a subgroup of G. So it means intersection of two subgroups is also a subgroup of G. Next comes the theorem. Union of two subgroups of G is a subgroup if and only if one is contained in the other. That is, intersection of two subgroups is a subgroup, but union of two subgroups need not be a subgroup. When will it be a subgroup means if and only if one is contained in other. So suppose if we have two subgroups H and K of a group G, then H union K will be a subgroup of G if and only if one is contained in other. What do you mean by one is contained in other? Either H subset of K or K subset of H. That is, H should be contained in K or K should be contained in H. So we are going to consider two subgroups of G. Let us name it as H and K. So we have two subgroups, namely H and K of a group G. We have to prove that H union K is also a subgroup if and only if H subset of K or K subset of H. So since this theorem is if and only if, we have to assume one part of the theorem and prove the other part of the theorem. And then conversely, we have to assume the other part and prove the first part, since it is given as if and only if condition. Now let us prove it. Now we are going to consider H and K be two subgroups of G such that one is contained in the other. So we have to consider it as H subset of K or K subset of H. But if we consider H subset of K, we can say that H is a subset and K is the superset. Every time the superset will be the greater than the subset. So if H is contained in K, then H union K will also be equal to K only. Similarly, if K is a subset of H, K is subset and H is a superset. So when you union K and H, you will get the answer as only H. So either H union K will be equal to H or H union K will be equal to K. But in our theorem it is given as H and K are subgroups. Now H union K is equal to either H or K. So now H union K also becomes a subgroup of G. So one part of the theorem is proved now. So we have proved that H union K is a subgroup of G. We have assumed that H is subset of K and K is a subset of G. Sorry, K is a subset of H. That is, H is contained in K or K is contained in H. We have proved that H union K is a subgroup of G. Now we have to move on to the converse part. In the converse part, we have to assume that H union K is a subgroup of G. And we have to prove that either H is contained in K or K is contained in H. So let us assume that H union K is a subgroup of G. So our claim is H contained in K or K contained in H. So we have to prove that H contained in K or K contained in H. Now we are going to assume the opposite category. That is, suppose H is not contained in K and K is not contained in H. We have to prove H is subset of K, K is subset of H. But we are going to assume it as opposite way. K is not contained in H and H is not contained in K. Then there exist elements A, B. We are going to consider two elements A and B such that if A belongs to H, then A does not belongs to K. We are assuming it as equation number 1. The next case is B belongs to K and B does not belongs to H. We are assuming it as equation number 2. Why we are assuming in this manner means we have assumed that K is not contained in H and H is not contained in K. So we can assume in this way. Now clearly A, B belongs to H union K because A and B both elements belongs to the union of two subgroups H and K. So A, B belongs to H union K. But we know that H union K is a subgroup of G. What does it mean? It satisfies the closure property. So now it becomes, since H union K is a subgroup of G, AB also belongs to H union K. We have considered two elements A, B belongs to H union K. Using the closure property, it becomes AB belongs to H union K. Hence, AB belongs to H or AB belongs to K. Because if we consider an element in the union of two subgroups, then either the particular element will belong to the first one or it may belong to the second one or it may belong to the both. So, AB belongs to H union K will imply AB belongs to H or else AB belongs to K. Now, the theorem splits into two cases. Either AB belongs to H or AB belongs to K. Two cases. Let us deal with the first case. AB belongs to H. So we have considered the first case AB belongs to H. Now since A belongs to H is a subgroup. So identity element will be present there. A belongs to H will imply A inverse also belongs to H. Inverse element also belongs to H. Since H is a subgroup, the identity element, inverse element all will be present there. So A belongs to H implies A inverse also belongs to H. Now let us consider the product of A inverse into AB. Using the closure property, we are going to combine this A inverse and AB. So A inverse into AB will become as B, since A inverse A is an identity element. Identity element into an element B will give you the same element B. Now B belongs to H, but in our equation number 2, we have considered it as B does not belongs to H. So now this becomes a contradiction to equation number 2. Now the next case. Let AB belongs to K. First case is AB belongs to H and the second case is AB belongs to K. Now since B belongs to K, the inverse element B inverse also belongs to K because K is a subgroup. So K will contain identity element, inverse element. So B belongs to K will imply B inverse also belongs to K. Hence AB into B inverse, just product of AB and B inverse will give A into B inverse. What is B inverse? Identity element. Identity element into any other element will give you the same element. So A into B inverse yields A, which belongs to K. But this is a contradiction to our equation number 1. Because in our equation number 1, A does not belongs to K. But this is a contradiction to our assumption. So where did we do wrong? Because we have assumed that K is not contained in H and H is not contained in K. So since we get a contradiction here, this is a contradiction to our assumption. So a conclusion is either H should be contained in K or K should be contained in H. Hence our assumption that H is not contained in K and K is not contained in H is false. Therefore, H is contained in K and K is contained in H. Hence, the theorem is proved. Thank you.